Welcome then to Chapter 1, Lesson 2. We start with a mind trap again today. Please do not think that the administration approves of underage drinking of martinis simply because this mind trap deals with one. But I am asking you to think a little bit outside of the box here. We've got 3 lines in a circle representing an olive in a glass. Minimum number of lines you have to move so that the olive is outside the glass. You can pause and think about this a little bit. I would suggest you remember the picture of the woman we had in class the other day, where I asked you to think outside of the box. That's what you need to do here. I hope you paused to think about this a bit. Did anybody come up with this answer? The answer being 0. You wouldn't have to move any lines if you do something like this. Well, why begin with this? Well, this is a good example of what we're talking about today. Angles. Angles, we're going to be measuring them, naming them, and so on, defining them. So let's get started. We have to begin with the idea of a ray. A ray, well, you look at it. What does it look like? Does it look at all like a segment or a line? Ask you to compare them a little bit. First of all, compare it to a line. Maybe you could pause here for a bit, think about that. It's really good to do that. When I suggest you pause and think a bit, you should do that. Challenge your brain. See if you can come up with the right answers. So hopefully you're back now. You thought about it. How is it like a line? Well, I can see a whole bunch of, well, there are an unlimited number of points. I can't see them all. Unlimited number of points in here. We've chosen 2 of them and named them with P and A. We do that on a line. We're doing that on a ray. Similarities probably stop there. How are they different? Well, if you remember yesterday, a line continued indefinitely in both directions, where you see a ray only goes on forever in one direction. So we've got an arrow on one side. I guess one endpoint, no endpoints on a line. Yeah, that's probably a good way to compare them. How about a line segment? Pause there quickly. I think spacebar should do it, and think about it a bit. If you're back, again, it's both made up, both a line segment and array made up of an unlimited number of points. Both use, you can name whatever letters you want. We've named 2 here. In a line segment, we named 2. But of course, the big difference in array, it goes on forever in one direction, where the segment had 2 endpoints. It stopped on both ends. If you were going to name this ray, how would you do that? Did you try it for yourself? Would it be ray PA and ray AP, like we did yesterday with a segment? We said segment PA and segment AP, which we could do with this picture, by the way. Or line PA or line AP if it went on forever in this direction. Well, with the ray, you got to be a little bit more careful. This ray, we could name PA, or we could name it ray P. As you can see, the important part is to name the endpoint in there somehow. And if you're going to use 2 letters, the endpoint has to be first. Had I labeled this AP, it would suggest starting at A and running through P forever. Why do we start with a ray? Well, we need 2 rays to create an angle. Challenge yourself here. What are the 2 rays that form this angle? Hopefully you named them correctly. Ray PA and ray PB. And by naming them that way, you may have noticed that they both have the letter P in it, and that's important. Rays have a common endpoint, in this case P. So we're getting close to our definition. We have 2 rays, and they have a common endpoint. The only thing we're going to add to that is the name of that common endpoint. It's called a vertex. So when we talk about defining an angle, we say that an angle is 2 rays with a common endpoint or a common vertex. How would you name this angle? Please pause and think about it. See if you can come up with 4 ways of naming this angle. So you're back. I shouldn't have to pause that much because you're pausing. How did you name it? Angle P would be one way. You need to have the vertex in there some way. You could name it angle APB. If you remember in Geometer's Sketchpad the other day, we measured angles by using 3 points. We'd go AP, we'd get the vertex in the middle, B. Of course, then you could go the other way as well and say PBA. And what I find most convenient is if they have numbers involved. We could label that angle A. So here we are with a couple of lines that intersect. Ooh, what do you call two lines that intersect? I hope you remember that word. Concurrent, because they contain the same point P. And you recognize this. Yes, that is a protractor. How did you do with protractors in school? Did you have trouble with them? Sometimes troubles happen. One thing is the teacher always made sure to tell you, get the vertex on that little point. Usually it was a little hole in your protractor. Make sure you line up one of the sides of the angle on either this line here or going the other way. And then see where the other side, the other ray intersects, and then give the degree measure. Did you ever get confused and say, well, is it 50 or is it 130? It can't be both. Couple of ways you can think about that. Find where your first side is, and that has to be the beginning of the angle, so you wouldn't start with 180. You'd start with 0 and use the inside scale and call that 50. That's one sure way to do it. Another way is to say, well, I know what a right angle is. That would be a nice square one. That's 90 degrees. This angle is less than 90 degrees, so it's got to be 50. Couldn't be 130. So how about this question? Are they clueless? Actually, they're not. It's just a lot easier sometimes to do it this way. You need to put the vertex in the same spot, but as long as one ray, one side of the angle, lines up over here, you can simply take the difference between these two measurements. This is actually something we study later called the protractor postulate, which says the measure of an angle is the positive number difference of the coordinates. So you take 130 minus 60 and you get 70. What's nice about this approach is it doesn't matter which scale you use. If we take the top scale, 50 and 120, the positive number difference is 70. So it's pretty easy to measure angles that way. Just slap the protractor on, get the vertex there, subtract the two coordinates. You should have gotten a handout in class with this picture, and the point of this one is to get you to practice measuring with your protractor to make sure that you know how to use it for the rest of the year. So you should pause at this point, measure those angles. When you come back, I'll put the measurements out there. You're going to need to bring this back to class because there's something on the back you'll be working on for your assignment. So please do practice. Make sure you can do that. All right, hopefully you paused, you measured, and you're back, and these are the numbers that I came up with. Was there any confusion when you got to C, measuring angle C? A and B were pretty straightforward, but C, I'm assuming you just measured this angle, but there's also this angle over here, which is why I put in this second one, BCE. Notice how there's no confusion when I use 3 letters? And that's a point I want to make here, that anytime you have a possibility of multiple angles in one spot, you can't label it with a single letter. You need to use 3 letters. As a matter of fact, did you realize there are 3 angles here at this vertex? There's angle ACB, there's angle ECB, but there's also angle ECA, or we could call it angle ACE. You know what that one's called? It's called a straight angle, and its measure is 180 degrees. If you think about a protractor, it would be a straight line from 0 to 180. And another thing that we'll notice later on this year is that if you take this angle and put them together, we get that straight angle. And take a look at the measurements. 105 plus 75 gets you 180 degrees, or that straight angle. Back to a mind trap. Shadow's at it again, and he's examining an angle that's 14.5 degrees. Right there, 14.5 degrees. But he's got his magnifying glass. It magnifies everything 2 times. So, under the glass, how large would the angle measure? Pause, think about it a bit. Two possible answers, aren't there? It could be 29, which makes sense. It's twice 14.5. Or it could be 14.5. The same? Which one did you come up with? Well, consider this. Here I have that 14.5 degree angle, and here it's twice as large, but take a look at the angle. The angle would be the same. And if you think about it, there's a good reason for that. The angle is made up of 2 rays with a common endpoint. 2 rays, and what's true about a ray, it goes on forever. So it doesn't matter where you put these arrows, it's going to go on forever, no matter how long they are. So our vocab so far, first of all, some undefined terms. Can you name some? Some terms that we just accept as true without defining them, undefined. We had point, we had line segment, and we had plane. We just can't define them, we use them. We did have some definitions yesterday. We had the definition of collinear. Do you recall that? Collinear. What is it that are collinear? Yes, it's points. Points are collinear if there is a line that contains them all. Non-collinear, of course, with non in the beginning. Points are non-collinear if there is no line that contains them all. Coplanar, 3 points are coplanar if there is a plane that contains them all. And concurrent, we use that today as a review. Lines are concurrent if they contain the same point. Today we had a couple of new undefined terms. One of them was ray. We didn't really define it, we just looked at examples, and we're going to be using that. We talked about sides, and we talked about vertex, or vertices is plural, vertex is singular. They were part of our new definition of angle. An angle, of course, is 2 rays, which sometimes we call sides, with a common vertex. So that gets us to the assignment, which you should have by now, Chapter 1, Lesson 2. Author starts out with a picture and gets you to just consider that picture, try to figure out which one looks the largest, looks the smallest, which side, which angle, and so on. Then he wants you to measure to the nearest 1/10 of a centimeter. Okay, what is that? If you look at your ruler, the marks that are numbered are centimeters. The hash marks in between them are millimeters, but if you'll notice there are 9 marks, which makes 10 spaces. Each one of those then would be 1/10 of a centimeter. Next part here, maybe you had this frustration in math before trying to measure angles. A lot of times you'd slap the protractor on here and the other ray wouldn't go far enough, it wouldn't go through the other scale, so you're kind of guessing at it. Well, many of your books probably have this done already, but a good idea is, in this next section you can do that, you carefully trace triangle ABC on your paper, and when he says trace it, do it. Sweat the details, follow directions clearly, completely. But trace it in your book, and as I said, most of your books have that in already. Just be careful when you trace it. Notice I didn't get lined up very well here. If the sides of the angle are longer, it's easier to get a measurement. So make sure you do that on these and measure the angles. So you're measuring all 3 angles of the triangle. My favorite constellation, Orion. The hunter, maybe that's because that's my middle name. The hunter, these are his 2 shoulders, his feet. Here's a sword hanging from his belt. So we're using these points to look at some of our terms and do some measuring. First of all, what word would describe these 3 points? Little vocab. He's getting you to use the words. Now we're looking at the angle without measuring. Guess these two answers. Now with your protractor, measure. Again, if your book doesn't have them extended far enough, go ahead and do that for yourself. Here's another constellation, Big Dipper. Same thing. Trace it on your paper. Extend sides, measure angles. The other side of that angle measure that we used in the lesson itself has a piece of graph paper that has 4 units per inch. I found one for you and gave it to you. We're going to use that for the sliding ladder problem. Keep in mind that the ladder itself is 6 feet tall. In this case, it's going to be 6 inches. You're going to use your ruler for 6 inches. And each time the ladder slides, make sure you're using 6 inches of your ruler. It starts out in the safest spot right here at 5 3/4. Since there are 4 units in each inch, that would be 5 1/4, 2/4, 3/4, 4/4, or 6. So the ladder is going to slide down the wall. And as it does, you're going to be asked to figure out how far is it from the wall. And you're going to be asked to measure angles that the ladder makes with the floor and angles that the ladder makes with the wall. So that's what you're looking at here in numbers 24 through 30, I believe it is. The sliding ladder problem. Again, measuring lengths, distances, angles, and so on. When you get all through with that, they do ask you this one question, which by the time you get there, I think you'll figure that out. How big do you suppose each angle would be when the angles are equal? So he's talking about when you put the ladder in here, the 6-inch ruler, 6-foot ladder, what's the angle down here going to be and down here going to be? What will they be when they are the same? Set 3 then is kind of a nice problem. It may be sticky credit, but it's trying to, well, what does it say? Planet Mars was drawn in 1903, a long time ago, before high-tech equipment. It shows canals and cities that he thought were there, but built there by intelligent beings on the planet. I don't believe that. Suppose they had discovered that when the sun is directly overhead at Bodrotus, point B, it's 24 degrees from vertical at Aquae Calidae. So here's that image. So when the sun is straight overhead here, it casts a shadow of 24 degrees here. And if the distance is 880 miles, what's the distance around Mars? There's actually enough in that picture to help you figure that out. And it's similar to a problem at the beginning of our lesson in which Eratosthenes calculated the circumference of the Earth 240 BC, way before a lot of scientific equipment. All right then, make sure you work through this ahead of time so you can ask any questions that you need to ask.